Hello students, welcome to fourth lecture of D and F block elements competitive. In previous lecture we discussed about ions and its compounds and properties of those compounds. In this unit we are going to discuss about the copper and its compounds. So from the earth crust we got different type of ores of copper. Those are copper pyrites, cuprite, copper glans, malachite and azurite. So we can abstract copper from these type of ores. And mainly copper is being extracted from its sulfide or copper pyrite. Now concentration of ore has a fourth flotation process, because if we have sulfide ore, then usually sulfide ores will be concentrated using fourth flotation method. So fourth flotation method is already discussed in metal abstraction unit. Then we have roasting reaction, in which main reaction is copper FeS2. CuFeS2 and O2 will convert into Cu2S and FeS. That means impurity of Fe will be removed as FeS. In side reaction, Cu2S and O2 will generate Cu2O, that means oxide of copper. In this case we have two different type of oxidation state of copper, +2 and +1. So lower oxidation state will be called cuprous and higher oxidation state will be called cupric. So Cu plus is cuprous and Cu plus 2 is cupric. Now same type of reaction will be done with FeS as well. FeS will convert into FeO. Now during the smelting process we need to remove FeO first, because Fe is more reactive metal than copper. So always first Fe will participate in each and every reaction. That's why we have to get rid of Fe first. So as we can see, in smelting process, FeO will combine with SiO2 and it will create slag. Slags are generally comparatively lightweight material. That means when we heat our substances and we melt them, then slag will float on the surface of molten material. So during this process, majority of FeS will convert in FeO and it will be removed in form of slag, but still we have some impurities of iron metal again. So that's why, as mentioned, the mixture of copper and iron sulfide melts together to form matte, and the slag floats on the surface. So in form of matte we still have impurities of Fe. Now next conversion of matte into blister copper. So silica is added to matte and a hot blast of air is passed, and FeO will combine with SiO2 and in form of slag it will be removed. By this time most of the iron sulfide is removed. So in different steps we will remove step by step impurity of iron. We cannot remove it in single step. So it is removed now. Then we have blister copper, which contains about 98% pure copper and 2% of impurities of other metals, silver, gold, nickel, zinc, etc. Then property, it has reddish brown color. It is highly malleable and ductile. It has high electrical conductivity and high thermal conductivity. That's why we are using copper wires in our regular electrical devices and to complete our circuits. And similarly we are using copper metals for cooling purpose as well. That means our mobile phones uses copper tubes for better cooling, and ACs uses copper tube for better cooling. Similarly, certain heaters also uses copper tubes and copper vessels because of better heating, because it can conduct a good amount of heat. So that's why we can use it in cooling purpose as well as heating purpose. Copper is second most useful metal after the iron, and it undergoes displacement reaction with lesser reactive metals, example silver. It can displace silver from AgNO3, because if we compare two different metals, then higher reactive metal has a tendency to convert into ions and lower reactive metal has tendency to convert itself into atoms. So if we compare the silver and copper, then copper is comparatively reactive than silver. That means copper and silver together, when they react, copper will oxidize, silver will be reduced. Because if we check the reduction potentials of copper and silver, you will notice copper has reduction potential of 0.33 and silver has reduction potential of 0.8, which is much higher than the copper. So that's why it can displace silver from AgNO3 and you will get CuNO3. The finally divided Ag so obtained is black in color. That means for abstraction of silver from its solution, we can use copper as a reducing agent. It can reduce silver. Copper shows oxidation state of +1 and +2, and copper +1 salts are colorless and copper +2 salts are blue in color. Now simple reason, if you check the electronic configuration of copper +1, then normal electronic configuration of copper is argon core 4s1 3d10. So when you get copper +1, one electron from s orbital will be removed, so now we have 4s0 and 3d10. So as we can see, we have d10 electronic configuration. If we have partially filled at d orbital, then we can get colors from this type of elements, but as we can see, we have fully filled at d orbital, so it cannot show color. But if we check the electronic arrangement of Cu plus 2, then it will be 4s0 3d9. So we have partially filled at d orbital in copper plus 2. That's why it shows blue color. Now these copper +1 salts are less stable and hence they easily oxidized into copper 2. So simple reaction 2Cu plus will give us Cu2 plus and Cu metal. So this reaction is called disproportionation, because in this reaction you will get higher oxidation state than the reactant and lower reaction state oxidation state than the reactant. So our reactant has +1 oxidation state and products have +2 and 0 oxidation state. So it is called disproportionation reaction. In presence of atmospheric carbon dioxide and the moisture, copper gets covered with green layer of basic copper carbonate. So it is one type of rust of copper which protects the rest of the metal from further action. So copper with oxygen with carbon dioxide and water gives CuOH twice CuCO3 green layer, so which will protect the remaining copper. That's why coppers usually do not get rusted like iron. In presence of oxygen or air, copper when heated to redness below 1370 Kelvin first form red copper oxide, which changes to black cupric oxide on further heating. So as we can see, cuprous oxide, that means it has +1 oxidation state, so it will be Cu2O. And next, black cupric oxide, that means it will have +2 oxidation state, so it is CuO. OUS, that means lower oxidation state. IC suffix, that means higher oxidation state. If the temperature is too high, cupric oxide changes back to cuprous oxide, and reactions are mentioned below. Then action of acid. Non-oxidizing dilute acids such as HCl, H2SO4 have no action on copper. However, copper dissolved in these acid in presence of air. So that means we need air or open atmosphere at least to get reaction of copper with acids. So as we can see, Cu with HCl in presence of air gets CuCl2. With HNO3 it gives CuNO3 twice. With HNO3 in different higher concentration it gives CuNO3 twice with NO2 gas released. With hot concentrated H2SO4 it gives copper sulfate. Now let's talk about the some compounds of copper. First is halides of copper. So we can get different examples of that, but usually we are going to discuss more likely used compounds. So copper to chloride Cu2Cl is prepared by the passing chlorine over the heated copper. Concentrated solution of Cl2 is dark brown but changes first to green and then blue on dilution. So on heating, disproportionation to copper 1 chloride and chlorine will be obtained. CuCl2 will give us CuCl and Cl2. Now let's check the oxidation state of all the species present here. So copper as a reactant has +2 oxidation state. Chlorines are in -1 oxidation state. After the reaction we have CuCl, so copper is in +1 oxidation state. Chlorine will be in -1 oxidation state, and our product, second product, chlorine, which is in 0 oxidation state. Okay, so these are the oxidation states. It is used as a catalyst in Decon's process for manufacturing of chlorine. Copper 1 chloride CuCl is a white solid insoluble in water. It is obtained by boiling solution of CuCl2 with excess of copper turnings and con HCl. It is dissolved in concentrated HCl due to the formation of complex HCuCl2. So between the Cu and Cl2 we have coordinate covalent bond, that's why they are mentioned in brackets. It is used as catalyst along with NH4Cl in the preparation of synthetic rubbers. Next, copper oxide. It is reddish brown powder insoluble in water but soluble in ammonia solution, where it forms diamine copper. Cu plus with 2NH3 gives CuNH3 twice. So it is complex formation. So it is used to impart red color to glass in glass industry. Next, copper oxide CuO. It is dark black, hygroscopic, that means water absorbing, and reduces to copper by hydrogen, CO, etc. It is used to impart light blue color to glass. It is prepared by heating copper nitride, CuNO3, and on heating it gives CuO and it releases NO2 gas and oxygen gas. Next, copper sulfate, which is also known as blue vitriol because it is blue in color. When we make solution of copper sulfate, it turns blue, otherwise it will be white. That means when we have pure copper sulfate, it will be pure white compound. If it absorbs water or if we dissolve it inside the water, then it will form complex compounds with water as a ligand. So water molecules will act as a ligand. It will donate electron pairs in copper, and that's why complex formation occurs, and because of complex formation it gives intense blue color. So it is prepared by action of dilute H2SO4 on the copper scrap in presence of air. On the heating, it is blue in color as mentioned earlier because of presence of water. Okay, in solid state, when water is being absorbed or in form of moisture or other form, if water is present, then it will form complex compound. So heating, this blue salt becomes white due to the loss of the water of crystallization. So CuSO4 5H2O. Now this 5H2O is actually present as ligands and they donate electron pairs in empty orbitals of copper. And that's why when we heat it and we remove each and every water molecules from it, then you will get white CuSO4, which is colorless. So usually in laboratory we have copper sulfate as a white powder form. About 1000 Kelvin, CuSO4 decomposes to give Cu and SO3. It gives deep blue solution of tetraamine copper to sulfate with NH4OH. Again complex formation, CuSO4 with NH4OH gives CuNH3 4 times SO4, which is complex compound, and it will be tetrahedral in shape. With KCN, it first gives yellow precipitates of CuCN, which decomposes to give Cu2 Cn2. That means plus 2 to plus 1 change of oxidation state. Cu2 Cn2 dissolves in excess of KCN to give K3CuCN4. Again one more complex compound. So as we can see, as mentioned earlier, D block elements have very good tendency to form complex compounds, and here are few examples. As we can see, copper can form multiple different type of complex compounds. Similarly, previous example, iron can form many different type of complex compounds as well. With Ki, it gives white precipitates of Cu2I2, and reaction is mentioned. And next again one more complex of Fe with CuSO4. So with K4FeCN6, which is the complex compound of iron, CuSO4 gives reddish brown precipitate of Cu2FeCN6. So K will be replaced by copper. Now let's talk about the uses for electroplating and electrorefining of copper, that means purification of copper. So as a moderate in dyeing for making Bordeaux mixture, 2 parts of lime as a milk of lime and 16 part of copper sulfate in 1000 parts of water. It is an excellent fungicide, that means it can be used to removal of fungus for making green pigments containing copper carbonate and other compounds of copper like verdigris, which is copper CH3COO twice CuOH twice, that is basic copper acetate, and it is used as a green pigment in paints. And it is also used as a fungicide in starch paste for bookbinding work. That means for bookbinding, the paste which is based on starch, and we can add copper sulfate as a fungicide to prevent fungus. Then we have cupric sulfide, and it is prepared with the reaction of copper nitrate with H2SO4, and it can be obtained as black precipitates as mentioned. Then we have basic copper carbonates. Because of the lower solubility of the hydroxides, the normal carbonate does not exist. Two basic copper carbonates occur in nature, that is malachite, and it has a fine green color, and azurite, which has deep blue color. The malachite is prepared by heating the mixture of CuSO4 solution and limestone in scaled tube at 423 to 443 Kelvin temperature, and as the reaction suggests, at the lower temperature azurite is formed. So same type of conditions in different same type of reactants in different conditions. On heating, both decomposes to gives black cupric oxide, water and carbon dioxide. So they are used as a green and blue painter's pigment under the name malachite green and azurite blue. So these are the additional points for copper, and in next lecture we are going to discuss about the silver.